Hi, everybody. I'm Eric. I'm the lead Unix system administrator here at Sonoma State in IT. So I manage the email systems and main campus web server, a number of other servers like that. I'll put the slides up here. They're not there right this second, but you'll get to see some notes. They have some references, that sort of thing. And hopefully that's not going to work. Awesome. Well, I guess I get to stand over here. Hello? Oh. I really needed it to crash. Thank you. Can I turn the mic? What the hell? That's really annoying. Okay. And everything's hiding over here because it hates me. Wow. That is awkward. Hey, let's see. Does that work? Yay! Okay. Sorry about that. Gotta love when things crash on you. So first, I felt I should start with a few little disclaimers. It's all my own opinion. Nothing is an official Sonoma State statement, really. Unless it's a specific information like, how a protocol works, and even then it's pretty simplified, or how many servers we have, it's my opinion. A bunch of people have worked on this over the years. I'm not mentioning names. It would take too long. Sorry, Dustin. I'm also not really going to refer to the network, but everything relies on the network. And the networking guys, I don't think I see any here, but they shouldn't be too offended that I'm mostly leaving out the network equipment. And also, I have a life, and furloughs really actually affected that. I didn't have nearly as much time to prepare as I was hoping. So, I have this feeling that most people's idea of what email looks like is kind of like this. Alice wants to send Bob some email. You send it to the mail server. It sends it to the other mail server, and Bob picks up their email. Alice and Bob are kind of canonical example people. And that's too simple, right? That really doesn't explain what really goes on. And then I tried to document, with a diagram that and and I know you can't read it, but trust me, it won't help. It looks like someone sneezed spaghetti. And in fact, I left some bits out, and yeah. And I tried another approach for diagramming it. Yeah. So I'm going to try and work on it over here on the whiteboard in front of you instead. Build it up a little at a time. So here's an example email. Most people, I suspect, see this subject part and the body and maybe the date, and you don't look at all these other bits. We'll get to those, I think. So first, you've got, let's go. You've got Alice and Bob. Those, here, give them little legs. They want to send email. So the very first thing that happens is not what you think at all. We've got this load balancer. And typically what will happen is you'll go to the load balancer and make a DNS query, because you don't know what the IP address of your very important mail server over there is. And we've got 3 of them over here, 2 and 3 little boxes. And it will randomly pick one of those and then send back your information. Or if that takes too long, actually the way DNS is configured on campus, you might go directly to one, or there's an offsite. Nothing works if DNS doesn't work, so we've got it quite redundant. And then you finally make a connection to an SMTP server through this load balancer here. Now, what the load balancer is some fairly expensive hardware that goes and checks which servers are up and dynamically assigns your connection to one server or another. We're actually hoping to replace it with one that's a little smarter soon. So you make your connection to a random mail server, let's say Krusty. Yes, that really is one of the names of one of the mail servers. It's with a K, like the clown in The Simpsons. There's a theme here. Actually, I should have said Nelson. That's the example I used here. But so Nelson wakes up and says, "Oh, hello, nice to see you. I'm Nelson. I support SMTP. I'm running XM. Here's the date, in case you didn't know the time." I don't know why And then I say hello, except I want to say that I support the new version of the protocol, not the old version, so I swap the E and the H and say it with kind of a funny accent. Hello. It's extended hello, I think, but I like to think of it more as an accent. And then I say my host name. I'm leaving out all the .sonoma.edus because it didn't fit. Then it responds back, says, "Oh, well, hello. Here's your IP address. I know who you are." One of the extensions that says how big of an email it will accept. That's convenient. Start TLS. I'm kind of going to skip over that one because it's complicated, but most users are actually going to be using that. That's how you initiate an encrypted connection. And we only allow you to authenticate if you're encrypting. But trying to show that in a nice slide format is not very easily. And apparently it even supports help. The little status code 250 tells it it's done. And I say, okay, well then I'd like to send you some email. I say mail from, so that's who's sending the email. This is the beginning parts of the envelope. Email has an envelope and then the actual header and the body. The envelope you usually don't ever see. But it's there. It's kind of like a letter. You tear open the envelope, you've got the piece of paper inside, you throw out the envelope because you didn't really care. Responds back and says, okay, that looks good to me. Our servers, in some cases, if I said I was coming from, say, my normal email address, it would not say okay because I hadn't authenticated. Most of our users are required to authenticate in order to send emails themselves. But here I'm sending it from my desktop, telling it it's an email from my desktop machine. I say who it's to, recipient to eric.eisenhart@sonoma.edu, my own email address. Apparently I like talking to myself. If you'd like, you could pretend it's Alice and Bob, but I actually, awesome, captured some working examples to make sure it really all worked the right way. And it says, okay, that's fine. I know how to handle that email address. If I was coming from off campus and told it a non-campus email address, it would go, wait, what the heck are you talking about? I won't take that. Or if you're authenticated and sent to an off-campus address, it'll go, oh, okay, we'll queue that up for you. Then I say, okay, I'm going to send you some data. It says, okay, go ahead, send me some data. End it with a period on a line by itself. This is the email I actually sent you saw earlier. I set the subject. It's just a test, a dot to end it. It says, okay, and it tells me this thing that looks kind of like line noise or something, random looking string. That's something that hopefully, under normal circumstances, ends up in the logs on both sides of the connection, and you can track down where email really came from. And then I say quit, and it signs me off. So here we've got this part. So that's that connection right here, right? You sent the email. Now, later, Bob is going to pick up their email, right? Well, first, these servers that we have here, there's actually 5 different servers. They don't really have much in the way of local storage. They certainly don't have a terabyte of storage. They've just got some little hard drives. We've got, over here, some storage, which we'll get into a little more detail. So it goes and sticks it on the storage for you, right? And then later, Bob comes along. And, well, there's a couple different protocols for reading your email. Oh, I should have mentioned, by the way, SMTP Simple Mail Transport Protocol. There's also Mail Submission Protocol in the look identical. Mail submission protocol is a really limited form, but it supports all of these things that we're showing here. SMTP has a whole bunch of other options that mail submission protocol eliminates and aren't really important for most people, but you know. So, not very many people use the post office protocol, but we still support it. Post office protocol really is a fairly simple way to pick up your email. All it does is let you connect, authenticate. This, by the way, is an example I actually pulled directly from Wikipedia because it was a little bit too much pain to pull out. You get the status. Okay, I've got 2 messages, 320. List what they are. It tells them IDs, how big each one is, and then you tell it to transmit one. There's no support for folders in POP. It's really just designed for you connect, you download your inbox, you delete everything in the inbox, and you're moving the email from the server to your local client. And that's why most people don't use it. It doesn't work at all well if you ever use a different mail client than your primary one. Your email isn't there, right? It's only on it's only on your regular mail client. So here's an example. We transmit one of them. Pretend in there that you saw the 30 lines of actual email, and that's a short one. And then we delete it, and then we quit. I probably should have, grabbed the other one and deleted it as well. What people mostly use is IMAP. And by the way, that all previous would have been over an encrypted SSL connection. IMAP is way more complicated, and I'm trying to show. So first, you connect to the IMAP server. In this case, we'd be doing an encrypted connection. You can also connect unencrypted and initiate the encryption after you connect. It tells you a bunch of things that it's capable of because there's all these extensions. And in particular, it tells you what kind of authentication it supports. If you don't know what authentication it supports, then you don't know what you're doing. Now, here, this is great. Here's my username and password, right? Except it's encoded in base 64 and has some nulls. And no, that's not really going to get you anywhere. It's just the alphabet. You tell it what kind of authentication. But this is one right here, right? Well, IMAP, everything you do, you send, before the actual command, you send an arbitrary identifier. And then the results from that respond with the same arbitrary identifier somewhere in the response. The theory that I don't think many clients actually use, but the theory is that you could then just spew like 30 different commands at the server, and it could respond out of order. Like the SMTP, it's pipelining, it's going to respond in order. This, it could respond out of order because each response has the ID of the command you sent. So apparently it likes my password. It says, OK, login OK. Now here, I could list all the different folders I have. If I'd done that, the list would be really huge, trust me. I have a lot of mail folders. Everybody has an inbox, so I tell it to select the inbox. It tells me a bunch of crazy things about the inbox. Now, first it tells me what flags it supports for each message. It can flag a message as being draft, answered, you replied to it. Flagged, a lot of mail clients, this little thing, you click the little flag or the star or whatever. Deleted. When you delete messages, they are marked as deleted. They're not removed. That's a later process that they get purged, which probably confuses the heck out of people trying to clean up their email when they were told they were over quota. Seen tells you whether or not you've seen the message before. If you read it, the little N changes to nothing, telling you've read it. And then recent. Basically, once you look in your mailbox, the recent flag goes away. If you look in the inbox. And then it tells you which flags are permanent, i.e. you can set them and they'll stick. And recent is the one that's not in the list, because recent automatically goes away as soon as you list the messages in your mailbox. It tells me that I've got 751 email messages in there, one recent since I last checked it. And that tells me some things that I actually didn't bother reading all of what they are. But seriously, I don't know what the ACLs and I believe the read-write tells me I can actually write to this inbox. You could possibly have a read-only mailbox somewhere. For instance, some people have servers set up where there's a shared mailbox. Stuff comes in, lots of people read it, but they don't have access to read it. That would be a good place to put like announcements or special messages. The UIDs, every message in IMAP has a unique ID. It assigns them. So then I tell it, and note also the to, I set a different unique identifier and it responded with that same unique identifier in its response. Then I tell it I want to fetch the very first message. IMAP, pop just lets you basically fetch the message and then delete it. IMAP actually has support for all sorts of ways to break the message up into different parts. You can fetch just the headers, you can fetch just the subjects. For instance, fetching just the minimal information is usually used to list it. You fetch the subject, you fetch the dates, some other headers, who it's to and from, and then it lists those subject lines. And then it actually fetches the full message when you click on it in your mail client. Here, I'm telling it I want to fetch the first message, and body with just the empty square brackets means I want to fetch the entire thing. I could specify specific portions. I could tell it to give me a dump of the tree, like if it had attachments, and then just fetch one attachment. I don't think most mail clients do much more than just fetch the whole message and do all that work themselves. But and then it responds, okay, I'm going to fetch message 1. Here it is. It's 2,390 bytes. Then it sends the full message, which, again, I didn't include because it's way too long. And then it tells me, okay, we're done. And I log out. Nice and simple. So Bob, over here, has managed to connect to an IMAP server, right, through probably a different mail server. How about Chalmers? Superintendent Chalmers. And picked it up from the same storage. But where on the storage did that come from, right? I mean, it's just a big pool. So what we actually do here, locally, we have what we call LDAP. Or not what we call it LDAP. We have our LDAP servers. And most of our users don't connect directly to LDAP, but you can actually configure it to get some directory information. These servers here, so Chalmers or Krusty, go and connect to the VIP, the virtual IP on the load balancer. And you connect to Moltar or Zorak. Hopefully somebody watches Late Night Cartoon Network. And yes, those really are the names of the servers. And in the case of this sending here, what it searches for, when you're sending the email, it searches for the mail local address, eric.eisenhart@sonoma.edu. And then it fetches some other information, but mostly it looks for this directory here. And we just store that. We also could kind of compute it, but and when Bob connects, it looks for the user, or well, in my case, Eisenhart, look for the matching user ID that I want to match as. I'm not showing any of the password stuff here, and you don't actually pull the password stuff from the IMAP server. You attempt to see if your password works on the LDAP server instead. So the IMAP server can't dump everybody's password. It can only verify that the password you're trying is valid. And in that case, it would again pull this folder information. And here, we start getting a little more, I'll start diagramming a little bit more of the complexity here. So our storage is actually two separate storage arrays. We called them Jekyll and Heckle. They're connected, however. They're a clustered connection. So the actual hard drives back here, technically Heckle can access Jekyll's storage and vice versa, but under normal operation you access this server, this one, or this one for the storage that's on that particular server, that particular storage server. They're connected so they can all get to each other's storage so that if one of them goes down, nobody notices, frankly. We can actually reboot one of these, patch the operating system. No one notices. The downtime for email is like maybe a half a second. That half the people's email kind of locks up. No one's going to notice that. So this path here, this one is on Jekyll. And we've broken out the store. You could conceivably put just all of these usernames right up in the Maildirs folder. But then you'd have a folder with 10,000 subfolders. And it turns out when you list that, it's slow. For some reason, right? Or we want to scan through it. And at one point, we actually had it so that it was, so that like I would have been in E/Eisenhart, right? And that worked great when we had a few thousand users on it, because then you'd have a folder with a few hundred, you'd have 26 letters. But then the subfolders started getting kind of crazy, because you'd have 2,000 subfolders, and that actually takes a long time to pull that folder. So what we've actually done here, which I think is kind of crazy, almost all of the software here relies on just reading from here. But this is actually the first 2 digits of the MD5 checksum of my username. So what is it, 64 folders that we've got at that level? That happened to work out a little bit better for spreading everything evenly. Also because the alphabet, a lot of people have last names that start with the same thing. So you see a lot of stuff in S and J, and I forget the other directories, and like there'd be like 3 people in X. This spreads it out much more evenly. It's still kind of uneven, but they're only as bad as one folder being twice as big as the other, not 100 times as big. Nicely evenly spread out. Next, the actual format that we actually store the messages in on there. In the old days, with Unix email systems, typically what you would have had is your inbox would have been one really big file, just a single file, and you just tack a message onto the end of that every time a message comes in, right? The problem is that means if you're going to deliver 2 messages at the same time, or you're going to read messages while something else is delivering, you're locking it constantly. Locking is bad. Because locking means, at least if you can, if you have to lock, you need to lock. But locking is bad because if you have to lock, you have to wait. And if you have 10,000 people trying to access the same thing at the same time, and you've just suddenly made it so they all have to wait in line after each other, that'll make everything really slow. So what we use is a format called Maildir. Actually, we're using Maildir++, the extended version. The inbox actually consists of this temp, new, and cur. Each message is these funny-looking files in there. So in this one, I'm showing one message in the inbox. Actually, 2 messages in the inbox, one that I've read already and one new one. The normal method of delivery is a message. It generates a unique file name. The file name is the number of seconds since January 1st, 1970, which is how Unix keeps track of time. Some kind of arbitrary stuff here that's unique. It's actually the milliseconds part of the time first, and then the process ID. So this part, so right there, that should basically be, that's unique. And then you add the host name. So between the host name and the very precise time and process ID, plus sleeping for a whole millisecond just to be sure that this one never matches, that's a unique signature. Nothing else is going to generate that same file name unless like your clock goes backwards, which it shouldn't. But it could. There's a little extra precautions they take in case of that. So it writes it into temp and moves it into new when you deliver a message. And then when it's in new, that's where the IMAP or POP client is going to look. It's going to look in new or cur. And as soon as you look at the folder, it moves from new to cur. Also, we stick this nice little S equals 3593. That's the size of the message. We do that because on Unix, when you get a directory listing, right? You get the file names, you get the magic underlying ID, the inode. Well, in this case, this means we just have to look at the directory listing. We know from the file name how big it is if we want to deal with your quota. We don't have to, instead, if we didn't have that, we'd have to do a stat. We'd have to ask it for the information about each file, which is cheap, but when you're doing it for 100,000 messages, it's expensive, right? So we avoid that. We stick that here. And All of the operations that are done on these are what are called atomic operations that are safe to do for multiple clients at once. Rename on Unix either works or it doesn't. There's no halfway in between. It renames the file, it's done, right? Or you try to rename it and somebody else already renamed it, you fail. Similar with delete. You delete it, it's gone. So you read your email, it gets moved from here to here, which moving from one folder to another on Unix is just it's considered a rename. It's still atomic. And these little bits here at the end, those are those flags that are supported earlier. This means I've replied to it, I think, and I forget what the S means, actually, suddenly. Did I note that? No, I didn't. So the inbox is the temp, new, and cur. The gray so I think everybody here has gray mail, because that's where we send all your spam, or at least we try. So each folder starts with a dot, and then the folder name, and apparently I left out the L there, and then cur, new, and temp. If you have subfolders, they're separated with a dot. So really, it looks to you like there's folders that have subfolders. On the server side, there isn't. You could have technically a subfolder with no parent folder because of the way the server actually works. These aren't inside of each other. They're just all in one big directory, right? Apparently, most mail clients are confused when you have subfolders with no parent folder. I don't know why. And we use this because there's no locking, so that you can be accessing that same folder from a bunch of different places. You deliver, you read at the same time. Nothing ever has to be locked. We rely on the file system. And also, the file system protocol we're using, locking is even a little more, is kind of expensive and didn't used to work very well, actually. So we don't. So let's talk about the requirements, or the problem we were trying to solve. So first off, in January 2004, the provost sent this nice letter to the campus that told us that email was now official. That meant it has to work. Well, before that, PeopleSoft wouldn't send you email. They needed an official policy that it was an official communication in order for, say, your professor to be able to assume that you have a university email account. And so what that means, of course, is that everybody relies on it. Trust me, when it's down, people call. They assume it's there, kind of like you assume the ground's there, the air is going to be there. You know, it's really important. If the ground's not there, life sucks. But same with email. But most of the time, people just assume it's going to be there. You could even say they're addicted to it. You know, just like the crack addict, they get very upset if it's not there and they don't have their supply. So, the other part of the problem, growth. We don't know what kind of where that's going, but everything keeps getting bigger on here. The population was going up. That is, we kept letting in more students. Apparently, this year, that assumption is false. We're no longer letting in more students than the previous year. That's kind of also storage. Now, I grabbed a few snapshots. Back in 2004, we were using about 300 gigabytes. A few years later, we doubled that. A couple of years after that, we almost doubled that again. We're just under 1.4 terabytes now. And most of those are like 10K each. There are a lot of little teeny files. Spam, well, spam keeps growing. I'm not sure if you've noticed. Yeah. And we've actually seen, so here is actually a graph of email deliveries that we've made on average since August 2006. This is the email deliveries per second that we make. The yellow and orange colors here, those are deliveries to your inbox. These gray, different shades of gray, are deliveries to your spam box. Around here, we actually changed and got a separate appliance that actually stops some of the spam from ever reaching our servers, which is why that's, I believe, why that's gone down. And when we were designing this, designing where we're at, we were kind of here. It kind of looks like it's swinging up. Apparently, it leveled off. I was shocked. And the other thing is for the and note that's the scale there at the very top. The top number there is 6 per second. So, and this is an average over the whole day, checking every 5 minutes. So, it basically barely ever gets. Apparently sometimes way back then we get under 1 a second in the middle of the night, but in general. Here's that same data. I had to change the colors to get some better contrast. This is the maximum 5 minute per 5 minute interval over that same time period. And instead, so that means we have peaks of each day of at least 10, often 20, 30, sometimes 50. That means that's what we have to design for as far as the ability to handle how many operations we handle, right? This nice average, that'd be great, 1 a second. But no, we got to worry about 60 per second coming in. So I assume you're all familiar with Moore's Law, right? Moore's Law, this is graphed logarithmically, so it doesn't look all curvy. It's a nice straight line. Every 18 months, chips get about twice as fast, or technically the density increases. And, okay, the color shift. There's Moore's Law. Kreider's Law is another one somebody wrote. They noticed that hard drives got bigger. The areal density that you could fit on there got doubled every 12 to 13 months. So that outpaces that. Now, on a hard drive, because down here, what we've got is a bunch of hard drives. Each of these little circles is, I'm thinking of as a shelf. They're 15, so there's about 60 hard drives. They're not all 60 are exactly dedicated to email. There's some RAID, but so Moore's Law is approximately relates to your maximum transfer speed. If the hard drive already has it in its cache, that's how fast it'll send it. I'm really simplifying here, but those tend to keep in pace. Kreider's Law, that's how big your hard drives are. We used to buy 9 gig hard drives. You can't find one of those anymore, right? I remember being excited when a 1 gig hard drive came into existence. Now I've got one 4 times that size and a little thing in my pocket. Disk seek speeds, on the other hand. So let's draw a hard drive for you. Really simple version of a hard drive, right? It's a little spinning platter. Spins at some set speed, and there's what we call an actuator, which is a little arm with a read head, and it swings back and forth, right, somewhere in there. The access time, if you don't know what block you're going to access, and so you get a request for their hard drive to access it. The access time is how long it's going to take for, if it's this block, for that to swing underneath the actuator arm and for the actuator arm to move. That's increased very slowly comparatively. Hard drives have not gotten a whole lot faster, how fast they spin. And that's kind of bad for us because that means our problem here, right? We've got 10,000 people checking their email pretty often. And we never know what the next message they're going to request is. So we've got a problem of randomly accessing things. So if we just keep buying bigger hard drives, well, then we're dealing with the ratio of those two laws, this one, the top one, and that's been going down. The random access time to randomly access a large number of blocks on a hard drive is going down because the hard drives are getting bigger. If you've got 2 500 gig hard drives versus one 1 terabyte drive on the same speed, you might be better off with a whole bunch of little ones. So we actually have a bunch of 136 gig drives here. 1 terabyte drives would be too slow. So those are the really basic parts of the problem space we were working in. So we had some limits first. The biggest one, money. Apparently, for some reason, they're not going to give us $1 million every year to do this. We could make a really great email system for $1 million a year. And it's not just how much money we get, it's also the relationship between the money and the email. If you were running, say, Google's email, where every time someone looks at an email, there's an ad, they know how much revenue they're making, right? This is a cost center. It doesn't make any money for the campus, right? They rely on it. It's important, but it doesn't make money directly. In fact, we're nonprofit based, so most things don't make money. The other thing here is people. The university has a general policy to never lay off. What that means is that hiring people is a commitment. Buying stuff is not. It's way easier to buy $200,000 worth of stuff than to buy a person that costs $100,000 a year, because there's a commitment. Our staffing, if anything, keeps going down because, yeah. So, hello. Awesome. Oops. There we go. I hit the wrong button. Okay, so the goals that I tried to establish with this, first, it has to be reliable. The other part of our staffing is we're basically an 8 to 5 shop. There's one guy that shows up at 6:30 in the morning, another guy that's there until 6 p.m. On a Saturday, there's no one there. If it's broken until Monday morning at 8 a.m. But we still have people teaching classes in the evenings when there's no one here to support it. It basically has to work on its own. It has to be highly available. That's why we've got, these load balancer here that I refer to. There's actually 2 of them. If one of them fails, the other one takes over. All these servers, we have more than one, and they're redundant. So if one fails, the other ones take over. You never notice. We reboot one of these in the middle of the day. I did that just a month or so ago, and no one noticed. The money, we have to try and, one of the goals with our current system, we're trying to get something that would actually work for a few years without having to keep going back and asking for money again, because it's a lot of money, and they don't like giving it to us. In concurrency, we need to be able to handle, all these things happening at once, which, pretty much another way, asynchronous. Most, all this stuff without the locking, you don't have to run things sequentially. They just come in any order, and they work. So, what do we actually run? Well, first, hardware. The mail servers, we've got 5. They're 8 gigabytes of RAM, dual-core AMD chips, 2 of them each. They're actually way over spec for right now. I'm trying to buy them for about 5 years from now, or 3.5 years from now, I guess. But 5 years out from when we bought them, so we didn't have to buy them again. The LDAP servers, these are ready for replacement. They're old. There's 2 of them. They've got 2 gigs of RAM. They're kind of old and slow. There's also a master where you actually write your data, or where your password goes, for instance, and it gets replicated over there. These are read-only. We've got the 2. I left out webmail, didn't I? So webmail, we've got two webmail servers, right? 2 of them. And the webmail servers are actually just mail clients. They run squirrel mail, but all they really do is they connect to IMAP over here, and connect to SMTP. From my perspective, they're just like another mail client. They happen to be a mail client we're running. We also have mailing lists. I don't know if any of you are on any of the campus mailing lists. Some classes are using them. We have a little server, Mojo. When you send email to a mailing list, it notices that it's on a mailing list, and then routes it over to the mailing list server, which then sees who's on the mailing list and explodes it back with a lot of messages, because, of course, mailing lists rarely have only one person on them. And that's a virtual machine. Same with the webmail. I'll have to talk about that in a second, I suppose. We also have a small MySQL server that's actually currently only used for the webmail. And the storage. We actually have a bunch more hard drives than that hooked up, but those are the kind of hard drives that we're using for this. Now, I mentioned the rotating hard drives. These hard drives are the fastest we could get at the time. They rotate at 15,000 RPMs, rotations per minute. Most consumer hard drives are under 10,000. The bigger ones tend to be like 5,400, I think, these days. So we're going about 3 times as fast as most hard drives that you can buy, and they're small. They're only 136 gigs. We can't even actually get that size anymore. And then there's these load balancers. Now the load balancers, I run out of room, haven't I? The load balancers we're trying to replace. The current configuration, there are 2 load balancers, 2 firewalls, and then 2 more load balancers connected kind of like this, because the old firewalls didn't know how to handle their own load balancing or availability. Apparently they did a software update, and this configuration isn't necessary. So these are little clusters, like 3 separate clusters, essentially. That's going away and getting simpler because the new hardware is smarter. And I mentioned virtual machines, right? Has anybody here dealt with virtual machines before? Okay, so it's not too unfamiliar a concept here. In our case, we're running VMware ESX, or they've renamed that to vSphere for the new version. So what we actually have is, right now, is 5 servers, and they share some different storage pools, which are over here or on an older storage system. And an individual VM, like, say, Blinky, could be here, and it has some stuff where it will, what they call vMotion. It will actually dynamically move it to another one to reassign load between the hosts. It technically, I think, does it by pausing it for a second, but it manages to pause it for more like some number of milliseconds. Pauses the VM, starts the duplication, and then duplicates the very last bits that have changed at the last second. That also means for these 5 pieces of hardware, we can shut one down, everything dynamically moves, no one notices. We're really big on the no one notices when something goes down around here, because I think my boss is laughing about that one, yeah. So what do we run? So these mail servers here, right? The actual software we run, first we run XM, that's the SMTP server. It's simpler to configure than SendMail, if you've ever heard of SendMail, but a little more powerful than Postfix. Fairly simple. I don't know if you guys have encountered either of those pieces of software. It's open source. Actually comes from our OS vendor, Red Hat. We run Clam AV, which is an antivirus package. We're configured. If we scan a message, it looks like there's a virus. We simply refuse to accept it. We actually get very little in the way of viruses. If anything, I think we're running that to protect this from I/O. The users should all have their own virus package. In fact, I know most of the desktop users on campus that are faculty or staff do, and students in the dorms are supposed to have access to something, I think. I don't know all those details. So really, from my perspective, we're just trying to protect the storage system from being hammered by, sudden 100,000 emails. Like Susan Kashak, right? Okay, those are 10,000. We also run on here Spam Assassin, which is part of what we're using to flag. Ooh, I'm out of time, aren't I? Courier IMAP. Let's see. We already talked about the NetApp storage. Webmail is Apache, PHP, Squirrel Mail. The LDAP servers basically run some local code on CGIs that some of which you've used, like when you change your password. And there's a lot of custom code going on there. Brian knows all about that. MySQL server, pretty boring. It just runs MySQL. The lists, it's literally all it runs. It runs SSH, the other management things. The list server, there's a web server, and the Mailman software. We also have some secret behind-the-scenes things. We use Tsunami to track what all of these systems are, because it's actually kind of hard to keep track of all these servers in your head. And I didn't even list all of them. And there's a bunch of other ones that do other things. some in-house software that Brian back there wrote. Hi, Brian. We use software called Puppet to configure most of these servers. There's a few older ones we're not using it on yet. I could do a whole talk about Puppet. In fact, that was the other talk I was considering doing. The other part on the LDAP servers, there's a whole lot of code we call the registry. There's actually a separate database that tracks all that, and we kind of sync it over to LDAP, and we sync it over to some other systems, all that information. Let's see, spam. We actually have, for email that comes from off campus, we have some appliances that we bought from Red Condor, who's actually a local company, like they're in that old stuff Agilent used to own. And we have 2 appliances on site, and then they have hosted elsewhere more mail servers. So when mail is coming from off campus, it goes here, and then it goes from there over to our local servers to be delivered. And they're a lot smarter about finding spam than the stuff we did with Spam Assassin, because they can update it way more quickly. They've got people 24/7, that kind of thing. Let's see, what are things we've changed? The storage backend, we keep replacing that every couple of years. We started out with a little Sunbox, we replaced it with a bigger NetApp, with a NetApp, we replaced it with an EMC, which we called Bruno, and now we have this cluster. I already talked about changing the directory layout. So when I got here, we had kind of a mix of servers. We had 1 student server, 1 staff server, and we started to have the beginnings of the current system because Dustin and some other people had already been working on that. And I don't have time to talk about failures, do I? Damn.
Maybe you can come back next spring.
Uh-oh. But
There's pizza that is
uh-oh.
down rapidly.
Damn, I went too slow. I'll just say, if your load average spike graph looks like that, that's bad. Or that.